Please subscribe to support the channel. Astronomers have discovered something deeply intriguing. We might actually be living inside a cosmic void, a massive, underdense region of the universe where galaxies are unusually sparse. This isn't science fiction. It's a real scientific hypothesis suggesting that our corner of the cosmos, including the Milky Way, sits inside a gigantic cosmic hole that stretches nearly 1 billion light-years across. Such a void could subtly distort our measurements of cosmic expansion, possibly explaining why the universe appears to be expanding faster locally than it should. If true, this finding challenges the long-held belief that we live in a typical, average region of space and forces us to rethink our place in the grand cosmic web. If we truly are living inside a gigantic cosmic hole, the first question that naturally arises is, how could we not have known? How could humanity, after centuries of studying the stars, mapping galaxies, and measuring the universe's expansion, fail to notice that our own neighborhood might be an enormous underdensity in space? The answer lies in the sheer scale and subtlety of the cosmos itself. Voids aren't empty in the way a vacuum is empty. They're simply regions where matter is thinner, where galaxies are more spread out, and where gravity's pull is weaker than average. To beings like us, confined to a single galaxy and limited by the speed of light, such vast differences are incredibly difficult to detect. For decades, cosmologists have assumed a principle known as cosmic homogeneity, the idea that, on large enough scales, the universe looks roughly the same everywhere. This assumption has guided almost all of modern cosmology, from the equations describing the Big Bang to the models that estimate dark energy. But if we happen to live inside a region that's less dense than average, then that principle may not apply in the way we thought. The implications would ripple through everything we believe about the cosmos. Living inside a cosmic void can mean that many of our measurements, distances, redshifts, even the rate of cosmic expansion might be biased by our unusual vantage point. In effect, we'd be cosmic observers inside a gravitational bubble, looking outward and seeing the universe expand in ways that appear faster or slower depending on how matter is distributed around us. It's a bit like trying to judge the shape of the ocean while standing inside a whirlpool. The local distortions make it hard to see the whole picture clearly. And that's the heart of the mystery. If the universe is structured in vast webs and voids, what if we've mistaken our local underdensity for a universal truth? Could our observations of dark energy, or even our measurement of the Hubble constant, be influenced by the cosmic hole we inhabit? If so, the story of the universe's expansion and our place in it might need to be rewritten. As we venture deeper into this cosmic puzzle, it's essential to understand what these voids really are, how they form, what they look like, and why they matter so profoundly. Because to grasp the mystery of our supposed cosmic hole, we must first understand the nature of cosmic voids themselves. To understand how we might be living inside a cosmic void, we first need to understand what a void really is and how it fits into the grand architecture of the universe. The cosmos, as vast and chaotic as it appears, isn't a random scattering of galaxies floating through infinite space. It's structured, intricately, beautifully, and with a pattern that stretches across billions of light-years. When astronomers map out the universe in 3 dimensions, they find that galaxies cluster together in enormous filaments and walls, weaving an immense cosmic web that spans all of space. These filaments form the skeleton of the universe, long, thread-like structures of galaxies, dark matter, and intergalactic gas bound together by gravity. Between them lie the great voids, enormous, relatively empty regions where galaxies are sparse and matter density is dramatically lower than average. In other words, the universe is not a uniform sea of stars and galaxies. It's a web of light and shadow, where bright threads of clustered galaxies surround dark, nearly empty cosmic bubbles. When you zoom out far enough, this structure becomes breathtaking. The filaments connect like neural pathways, intersecting at vast clusters where thousands of galaxies gather. The universe's cosmic cities. Between these intersections are immense gaps, where only a few lonely galaxies drift in the deep dark. These are the voids, silent, ancient expanses that make up the majority of the universe's volume. In fact, astronomers estimate that more than 80% of the universe by volume is made up of these cosmic voids. That's right, the universe is mostly nothing. The galaxies, stars, planets, and all the visible matter we can observe are confined to thin, luminous threads that trace the boundaries of these vast, invisible cavities. What fills the voids instead is a tenuous mix of dark energy, sparse dark matter, and the faintest wisps of intergalactic gas. Cosmic voids form as a natural consequence of gravity and the universe's expansion. In the early universe, small quantum fluctuations in density, tiny ripples in the otherwise uniform cosmic soup, grew over billions of years. Regions slightly denser than average pulled in more matter, growing into clusters and filaments, while the underdense regions lost matter to their surroundings, becoming emptier and more vast over time. It's as if the universe sculpted itself, the rich regions becoming richer in galaxies, while the poor regions, the voids, were drained of their material. These immense voids come in many sizes. Some are tens of millions of light years across, others stretch for hundreds of millions. The largest can even span over 1 billion light years, dwarfing entire superclusters. They aren't completely devoid of galaxies, but the galaxies they do contain tend to be smaller, dimmer, and more isolated than those found in dense clusters. The voids are in many ways the cosmic deserts between the fertile galactic lands of the cosmic web. When we talk about possibly living in one of these voids, we're not saying the universe around us looks empty. After all, we're surrounded by billions of galaxies when we look deep into space. Rather, we might inhabit one of the less crowded neighborhoods of the cosmic web, a region that's slightly underdense compared to the cosmic average. It's a subtle difference, almost imperceptible without vast amounts of data, but it can profoundly affect how we interpret the universe's behavior. Understanding voids, therefore, isn't just about mapping emptiness. It's about decoding the very structure of the cosmos. These vast, silent regions are like the negative spaces that give the cosmic web its form, shaping how matter clumps, how light travels, and even how we perceive the expansion of the universe. And that brings us to an even deeper realization. These voids are not small. Their scale is almost beyond comprehension, vast enough to swallow clusters of galaxies whole and still have room to spare. So if we are living inside one, we're not talking about a small pocket of emptiness. We're talking about a structure of truly cosmic proportions. When we speak about cosmic voids, we're not referring to small gaps between galaxies. We're talking about structures so enormous that they defy human intuition. To truly grasp the scale, imagine this. Even the smallest cosmic voids can span tens of millions of light years. The larger ones stretch across hundreds of millions of light years. And in some extraordinary cases, they reach sizes of nearly 1 billion light years from one end to the other. These are not minor features in the cosmic landscape. They are among the largest known structures in the entire universe. For perspective, the Milky Way is about 100,000 light years across. A typical galaxy cluster might span a few million light years. But a cosmic void? It can easily be 1,000 times larger than that. If our galaxy were a single grain of sand, then an average cosmic void would be the size of a continent, vast, silent, and incomprehensibly empty. These immense voids occupy the majority of the universe's volume. While galaxies, stars, and nebulae paint the bright threads of the cosmic web, it's the voids that fill the space between, the cosmic backdrop against which everything else exists. And these vast expanses aren't just empty bystanders. Their very size means they play a crucial role in how the universe evolves and expands. You see, matter and gravity are inseparable in shaping cosmic behavior. In regions where matter is dense, like galaxy clusters, gravity pulls more strongly, slowing the local expansion of space. But in regions where matter is sparse, like in voids, there's less gravitational pull, and so the fabric of space expands more freely. The result is that voids expand faster than denser regions, slowly pushing matter outward and making the voids themselves even emptier over time. This difference in expansion rates might seem trivial, but on cosmic scales, it can profoundly influence our measurements of the universe's overall expansion. When astronomers measure how fast the cosmos is stretching, using light from distant supernovas or the redshift of galaxies, they assume that space expands uniformly, everywhere. But if our vantage point happens to lie inside a vast, underdense region, then our local measurements could be subtly biased. From our perspective, it might appear as though the universe is expanding faster than it really is, simply because our surrounding void is expanding slightly more rapidly than the cosmic average. This is where the scale of voids becomes more than just a matter of size. It becomes a matter of cosmological significance. A small void wouldn't make much of a difference to our measurements, but a truly massive one, hundreds of millions of light years across, could alter the way we interpret key cosmic parameters, such as the Hubble constant or even the inferred density of dark energy. Astronomers have cataloged many voids through large-scale surveys like the Sloan Digital Sky Survey, or SDSS, and the 2D Galaxy Redshift Survey. Some of these, like the Boötes void, are legendary for their size and emptiness. Boötes spans about 330 million light-years and contains only a handful of galaxies in its entire volume. Yet even that giant might pale in comparison to what some scientists believe surround us, a structure so large that it could reshape our understanding of local cosmic expansion. If the evidence is correct, the region encompassing the Milky Way, nearby galaxies, and much of our local universe may be part of a supervoid, a structure not hundreds, but nearly a billion light-years across. It's so enormous that it could subtly distort the paths of light from distant galaxies and supernovas, affecting the very measurements upon which we base our cosmological models. So when scientists propose that we might be living inside one of these vast underdense regions, they're not suggesting we reside in a small pocket of emptiness. They're suggesting that our cosmic neighborhood could be part of one of the largest known structures in existence, a region big enough to influence the very way we perceive the universe's expansion. And that's where the story takes an even more fascinating turn. Because this enormous region isn't just theoretical. It might already have a name, the KBC Void. In 2013, a team of astronomers, Ryan Keenan, Amy Barger, and Lennox Cowie, made a bold proposal that would ripple through the field of cosmology. What if our galaxy, the Milky Way, sits inside an enormous cosmic void? Their research, which combined galaxy surveys and luminosity data from the near-infrared spectrum, revealed something unexpected. The local universe appeared to be less dense in galaxies and matter than regions farther away. This discovery gave rise to what is now known as the KBC Void, named after the initials of its discoverers. The KBC Void wasn't just another small gap in the cosmic web. It was unlike anything astronomers had seriously considered before. Keenan, Barger, and Cowie were studying how galaxy density changes with distance from Earth, essentially how crowded our cosmic neighborhood is compared to the universe at large. And what they found was astonishing. Within roughly 1 billion light-years from us, the density of galaxies was about 20 to 50% lower than the cosmic average. Beyond that boundary, galaxy density seemed to return to normal. This pattern suggested that we might be sitting near the center of a massive underdense region, a cosmic bubble embedded in the larger web of the universe. If true, this would make the KBC Void one of the largest known structures in the cosmos, dwarfing the famous Boötes Void and rivaling the largest supervoids ever detected. And yet, the irony is profound. Despite its unimaginable size, we never noticed it because we're inside it. It's like trying to realize you're in the middle of an ocean without any landmarks to measure the distance to the shore. The significance of the KBC Void lies not just in its scale, but in what it might explain. If our local region is truly underdense, then our measurements of the universe's expansion, which depend on observing nearby galaxies and supernovae, could be systematically affected. Inside a void, the reduced gravitational pull allows space to expand a little faster. This could make it appear, from our point of view, that the universe is expanding more quickly than it does on average, precisely the kind of discrepancy seen in the Hubble tension. At first, the idea sounded radical. The cosmological principle, the assumption that the universe looks roughly the same everywhere on large scales, had been a bedrock of modern cosmology for nearly a century. To suggest that our own region might be significantly different was in some ways to challenge that foundation. But Keenan, Barger, and Kau didn't propose their void lightly. Their analysis was grounded in real data, carefully measured and cross-checked. They weren't claiming the universe as a whole was uneven, only that our local patch might be less populated than Roast. Since the publication of their paper, the KBC Void hypothesis has sparked widespread debate and curiosity. Some studies have found hints supporting it, others have questioned its size or even its existence. But whether or not the KBC Void turns out to be the definitive explanation, the idea itself has forced cosmologists to look more carefully at our surroundings, to ask whether our cosmic vantage point might be influencing what we think we know about the universe. And so, the KBC Void stands as both a scientific proposal and a philosophical provocation. If we are truly inside it, it would mean that our galaxy, our entire observable region, and perhaps our entire understanding of cosmic expansion are shaped by the emptiness surrounding us. It would redefine the meaning of local universe and remind us that even in the vastness of space, our perspective might not be as objective as we once believed. But what exactly does this mysterious void look like? How large is it? And just how deep is this underdensity that we might be living within? To answer that, we need to explore its size and location, and understand where, exactly, we fit within this enormous cosmic structure. According to the findings of Keenan, Barger, and Cowie, the KBC Void is not just large, it is staggeringly immense. Their analysis suggests that this underdense region extends roughly 1 billion light-years across, with our very own Milky Way galaxy sitting close to its center. To put that into perspective, light, the fastest thing in the universe, would take an entire billion years to travel from one end of this void to the other. On cosmic scales, that's an almost unimaginable span, a vast, underpopulated bubble embedded within the sprawling cosmic web. Within this enormous volume of matter, galaxies, gas, dark matter, the density appears to be about 20 to 50% lower than the cosmic average. That means if you could somehow compare a cube of space inside the KBC Void to an equal cube taken from a denser region of the universe, ours would only contain about half as many galaxies. This doesn't mean the region is completely empty, far from it. The Milky Way, the Andromeda Galaxy, the Virgo Cluster, and countless others still exist within it. But overall, the space between galaxies here is wider, the cosmic fabric a little thinner. We inhabit a relatively quiet cosmic neighborhood, far from the bustling clusters and galactic superhighways that dominate denser parts of the universe. Visualizing this is tricky, because from our perspective inside the void, everything looks relatively normal. We still see galaxies stretching in every direction, and we still observe the large-scale cosmic web far beyond. But when astronomers map the distribution of galaxies in 3 dimensions, a subtle pattern emerges, a gradual transition from a locally sparse region around us to denser regions billions of light years away. It's as though we're sitting in the center of a cosmic bubble, looking outward toward the thicker, more crowded filaments that define the walls of the void. The center of the KBC Void is believed to be located very near our own position, close to the Milky Way's location within the local group of galaxies. This alignment is what makes the idea so striking and so controversial. If we truly are near the center of such an enormous void, it raises fundamental questions about our cosmic significance. Cosmology is built on the Copernican principle, the idea that we do not occupy a special or privileged position in the universe. Yet, being near the center of a billion light-year wide underdensity sounds uncomfortably special, even if it's a statistical coincidence rather than cosmic design. The boundary of the KBC Void, where the galaxy density rises back to normal, seems to occur at roughly 300 to 400 megaparsecs from us, about a billion light-years. Beyond that distance, observations indicate the universe becomes denser and more typical, aligning well with the overall average density seen in cosmological surveys. Within that radius, however, we reside in what might be described as a cosmic basin, a region where galaxies are fewer, distances slightly stretched, and gravitational pull a bit weaker than in the denser surroundings. If this model is correct, then our local superclusters, such as the Virgo and Laniakea superclusters, are like small islands scattered throughout a vast, dimly populated cosmic sea. These superclusters may form part of the inner structure of the void, drifting slowly within an expanding underdense region whose gravitational influence is slightly weaker than the rest of the cosmos. This enormous bubble of space doesn't just define where we are, it could also shape what we see. Because of its lower matter density, light from distant galaxies traveling through the KBC Void experiences slightly different gravitational effects than it would elsewhere. This can affect redshift measurements, luminosity distances, and ultimately our interpretation of cosmic expansion. In essence, the very fabric of our cosmic environment may be bending our perception of the universe's behavior. So, if we are truly residents of a billion light-year wide underdensity, the KBC Void, then we're not just part of an ordinary galactic neighborhood. We're part of a grand, rarefied region of cosmic real estate, one that could be subtly influencing how we measure the universe itself. But to fully grasp the importance of this, we need to go beyond its size and shape. We must look deeper into what makes the KBC Void different: its density contrast, the key factor that determines just how empty, or rather how underpopulated, this enormous cosmic space really is. Despite the dramatic name, the KBC Void isn't a literal empty space or some cosmic vacuum where nothing exists. It's not a black hole or a region stripped bare of matter. It's simply a place where the density of matter is lower than the cosmic average. That means it contains fewer galaxies, less gas, and a lower concentration of dark matter than other regions of the universe. Think of it not as a total absence of existence, but as a thinning out of the cosmic web. A place where the threads of galaxies stretch farther apart, leaving wider gaps of intergalactic darkness between them. Astronomers estimate that the matter density within the KBC Void is roughly 20 to 50% lower than the universal average. That might sound like a small difference, but on the scale of the cosmos, it's enormous. Even a 10% shift in matter density across billions of light years can influence how light travels, how galaxies evolve, and how we perceive cosmic expansion. In a region as vast as the KBC Void, nearly a billion light-years wide, that 20 to 50% underdensity represents an immense missing mass, equivalent to the combined matter of millions of galaxies. To picture it, imagine the universe as a vast sponge. The denser regions, galaxy clusters and filaments, are like the sponge's thicker parts, packed with structure. The voids, on the other hand, are the air pockets, still part of the sponge, but with far less material. The KBC Void is one of those enormous air pockets, and we're living inside it. There are still galaxies all around us, but they're simply spread out over a much greater volume of space. What's truly fascinating is that even though we live in this underdense region, it doesn't feel empty from our perspective. When we look up at the night sky, we see hundreds of billions of stars, nebulae, and galaxies. Our Milky Way, our local group, and the Virgo supercluster are all here, within reach of our telescopes. But if we step back, not physically but conceptually, and look at how matter is distributed over hundreds of millions of light years, we start to notice that our cosmic neighborhood is indeed quieter and more open than others. This underdensity affects how gravity behaves on large scales. In denser regions of the universe, gravity acts like a brake, slowing down the expansion of space as matter pulls inward. In a void, where there's less matter to exert that pull, space can expand more freely. Over billions of years, this difference means that voids grow even emptier, as matter gets drawn toward the denser walls of the cosmic web. The KBC Void, like all voids, is thought to be slowly expanding, not because of some explosive event, but because gravity itself is weaker there. This has a subtle yet profound effect on how we observe the universe. Light passing through a void experiences fewer gravitational influences, meaning it may appear slightly redshifted, stretched in wavelength, as space itself expands. This redshift contributes to our measurements of how fast the universe is expanding. If we're situated in a region where expansion happens just a little faster than average, we might misinterpret that as the universe overall expanding faster than it truly is. This is one of the key ways in which the KBC Void could help explain the so-called Hubble tension, the disagreement between local and distant measurements of cosmic expansion. The density contrast, that 20 to 50% dip below the cosmic mean, might therefore be far more than a curious feature of our local universe. It might be the key to understanding why different cosmological measurements don't quite line up. It's a delicate effect, easy to miss without vast amounts of precise data, but potentially powerful enough to reshape how we interpret one of cosmology's biggest puzzles. In essence, the KBC Void is not a hole in the universe, but a gentle valley in the cosmic landscape, a region where the gravitational tug is a little weaker, where galaxies are a little farther apart, and where the rhythm of expansion beats just a little faster. And if our galaxy happens to lie near the center of this vast, subtle underdensity, then we may have spent the entire history of astronomy observing the cosmos from inside a region that quietly distorts our view of reality. And that brings us to one of the most intriguing consequences of all, how living in the cosmic void could make the universe appear to expand faster from our point of view. Could the KBC Void be the missing link in explaining why the cosmos seems to stretch more rapidly than theory predicts? Here's where things start to get truly fascinating, and where the implications of living in a vast cosmic void like the KBC Void begin to touch one of cosmology's deepest mysteries: the apparent acceleration of the universe's expansion. From our vantage point on Earth, when we look out into the cosmos, every distant galaxy appears to be moving away from us, its light stretched to longer, redder wavelengths, evidence of the universe's ongoing expansion. This observation, first made by Edwin Hubble in the 1920s, became one of the cornerstones of modern cosmology. Later, in the late 1990s, astronomers discovered that the expansion wasn't just continuing, it was accelerating. The farther away a galaxy is, the faster it seems to recede. That acceleration was attributed to an enigmatic force now known as dark energy. But what if part of that observed acceleration isn't due to dark energy alone? What if our measurements are being subtly skewed because of where we happen to be, inside a massive underdense region of the universe that expands faster than its surroundings? In a region like the KBC Void, where the density of matter is lower, there's less gravity to slow down the expansion of space. Over cosmic timescales, this means the void itself expands more quickly than the denser filaments and clusters around it. To an observer within that void, like us, the galaxies outside its boundaries would appear to be moving away at slightly greater speeds than expected. In other words, from our perspective, it could look like the universe as a whole is expanding faster, even if the global expansion rate is perfectly consistent with theory.
This phenomenon arises from a principle rooted in general relativity. Gravity and geometry are intertwined. Where matter density is high, space-time curves inward and expansion slows. Where it's low, space-time curves outward and expansion accelerates. Living in a vast underdensity means living in a region where space-time is, on average, less curved, allowing the metric of space itself to stretch more freely. If the KBC void is as large and as underdense as Keenan, Barger, and Cowie proposed, around 1 billion light-years wide and 20 to 50% below average in density, then it could cause exactly the kind of apparent acceleration that astronomers observe locally. Light traveling through this underdense region would experience less gravitational time dilation, arriving to us with redshifts slightly higher than they would be if space were uniformly dense. When cosmologists measure those redshifts and compare them to theoretical expectations, the data could mimic the signal of an accelerated expansion. Now, this doesn't mean dark energy doesn't exist. The evidence for cosmic acceleration on very large scales, from the cosmic microwave background, baryon acoustic oscillations, and distant supernovae, still points to some form of repulsive force driving the universe's expansion. However, the KBC void could amplify that apparent acceleration locally. In other words, our particular position inside this massive underdense region could make the expansion seem even faster when measured nearby than it truly is on cosmic scales. This idea has tantalizing implications for what's known as the Hubble tension, the discrepancy between the locally measured Hubble constant, the rate of cosmic expansion determined using nearby galaxies and supernovae, and the value inferred from observations of the early universe, such as the cosmic microwave background. Local measurements, taken within a few 100 million light-years, consistently yield a higher number, suggesting the universe is expanding faster than it should be according to early universe models. If we happen to live in a region that's expanding a bit more quickly, a natural consequence of being in a vast underdensity, that could explain why our local measurements appear inflated. Essentially, the KBC void offers a possible bridge between observation and theory. Instead of invoking new physics or exotic forms of dark energy to explain the discrepancy, it suggests that the difference might arise from something as simple and profound as our cosmic location. We might be standing in a rare spot that slightly biases how we perceive the universe's motion. It's a humbling idea. For decades, cosmologists have assumed that our cosmic perspective is average, that the universe looks the same in every direction and from every point. But the KBC void challenges that notion. It implies that cosmic expansion might not appear identical everywhere, and that local structure can imprint subtle distortions on our view of the universe's evolution. And yet, as powerful as this explanation sounds, it opens another door to one of the most debated issues in modern astrophysics. Could this local underdensity truly account for the Hubble tension, or are deeper, more exotic forces at play? To find out, we need to look more closely at this mysterious mismatch between near and far, a cosmic disagreement that continues to baffle scientists to this day. The Hubble tension is one of the most perplexing and persistent mysteries in modern cosmology, a tension that strikes at the very heart of how we understand the universe's expansion. Named after the Hubble constant, the number that describes how quickly galaxies are moving away from each other, this cosmic disagreement has grown sharper with every new measurement. In simple terms, astronomers are getting two different answers to one fundamental question: how fast is the universe expanding? On one hand, measurements taken from the early universe, particularly from the cosmic microwave background, the faint afterglow of the Big Bang, tell us that the universe should be expanding at about 67 kilometers per second per megaparsec. This means that for every 3.26 million light-years of distance, galaxies should be receding from each other at about 67 kilometers per second. These numbers come from highly precise data collected by the Planck satellite, which map the tiny temperature fluctuations in the CMB and fit them to the standard cosmological model known as lambda cold dark matter. But when astronomers measure the expansion rate using the local universe, that is, using nearby galaxies, supernovae, and Cepheid variable stars, they consistently find a higher value, around 73 to 74 kilometers per second per megaparsec. The difference may sound small, but in cosmology, it's enormous. too large to be explained by random error. It's as if the universe near us is expanding faster than the universe as a whole, a contradiction that has sparked intense debate and speculation. So, what's going on? Why does our local universe appear to expand faster than expected? One possible explanation, as proposed by Keenan, Barger, and Cowie, and later refined by others, is that our local environment, specifically the fact that we may live inside the KBC void, could be scaling our measurements. If our region of space is underdense by about 20 to 50%, then the local gravitational pull is weaker. In such a region, space expands a bit more rapidly than in denser areas. Therefore, any observations we make of nearby galaxies would naturally yield a higher expansion rate. In other words, the KBC void acts like a local accelerator, given the illusion that the entire universe is expanding faster, when, in fact, we're simply sitting in a cosmic bubble where expansion happens more freely. This doesn't mean the universe as a whole is expanding unevenly. It just means that our vantage point might not be representative of the cosmic average. Several studies have explored this idea in detail. Some cosmologists have simulated what the universe would look like if a billion light-year-wide void like the KBC void existed around us. Their results showed that such an underdensity could indeed cause a small but measurable increase in the local Hubble constant. Not enough to erase the tension completely, but enough to narrow the gap between the two measurements. In other words, the KBC void could partly explain the Hubble tension, providing a natural, non-exotic explanation for at least part of the discrepancy. However, the effect seems to depend heavily on the void's size and depth. A smaller or shallower void wouldn't make much of a difference. The region would have to be vast and significantly underdense to affect our measurements at the level we observe. This is precisely what makes the KBC void so intriguing. Its scale and density contrast are just large enough to potentially influence the data in the right direction. Still, the debate is far from settled. Many scientists argue that even a billion light-year-wide void with a 20 to 50% density contrast can't fully explain the difference between the local and early universe expansion rates. The void might account for a small portion of the discrepancy, perhaps 1 or 2 kilometers per second per megaparsec, but not the full difference of around 6 or 7 units observed in the data. That suggests that something beyond local structure might be at play. This has led to researchers exploring alternative interpretations, possibilities that reach beyond the idea of a local cosmic void and into the realm of new physics. One leading hypothesis is that the nature of dark energy itself might be more complex than we currently assume. In the standard model, dark energy is treated as a constant, an unchanging property of space that drives cosmic acceleration. But what if dark energy evolves over time, or interacts with matter in subtle ways? A dynamic form of dark energy, sometimes called quintessence, could potentially cause the expansion rate to vary across cosmic time, reconciling the two measurements without invoking a massive void. Another intriguing idea is that the laws of gravity might not behave the same way on cosmological scales as they do within galaxies or solar systems. Modified gravity theories, such as F of R gravity or scalar tensor models, propose that the force of gravity weakens or changes its character over vast distances. If true, this could naturally explain why the early universe measurements, based on physics shortly after the Big Bang, don't perfectly match local measurements made billions of years later. Some researchers even suggest that there could be unknown particles or interactions that suddenly alter the expansion history of the universe. For instance, early dark energy models propose that a brief burst of repulsive energy shortly after the Big Bang could slightly change the inferred value of the Hubble constant derived from CMB data. Others consider the possibility of extra-relativistic species, sometimes called dark radiation, that existed in the early universe and changed the expansion dynamics.
Then there are those who emphasize measurement uncertainties and calibration issues. Measuring cosmic distances precisely is notoriously difficult. Even a small systematic error in how we calibrate the brightness of Type 1a supernovae or the distance scale of Cepheid variables could shift the inferred Hubble constant enough to create an apparent tension. While most modern analyses account for these sources of error, some cosmologists argue that until we reach an even higher level of precision, it's premature to invoke either voids or new physics to explain the discrepancy. Ultimately, the scientific community remains divided. And that's part of what makes this debate so fascinating. The KBC Void offers a grounded, observational explanation that fits neatly within existing physics. No need to modify the laws of the universe, just recognize the structure we're sitting in. But others see the persistence of the Hubble tension as an opportunity, a clue that we might be on the verge of discovering something entirely new about the cosmos. In the end, the truth may lie somewhere in between. The Hubble tension could be a combination of both effects, a universe that's slightly homogeneous on local scales and governed by physical laws more complex than we currently understand. The void may contribute part of the discrepancy, while dark energy or new physics fills in the rest. Yet, to move from speculation to certainty, we need more data and better ways to map the large-scale structures around us. Because before we can decide whether we live in a special cosmic bubble or a universe governed by undiscovered forces, we must first understand exactly what our cosmic neighborhood looks like. That's where the next question naturally leads us. How do scientists actually detect and measure these enormous voids in the first place? Detecting something as vast and subtle as a cosmic void is no small task. Unlike galaxies or clusters, which blaze brightly against the darkness of space, voids are defined by absence, by where matter isn't. To find them, astronomers must look for the faintest whispers of emptiness, the quiet gaps in the grand symphony of cosmic structure. And that requires one of the most powerful tools in modern astronomy: cosmic mapping. At the heart of this process lies a simple idea. If you can map the positions and distances of millions of galaxies, you can trace the underlying structure of the universe. Every galaxy acts like a point of light on a vast cosmic graph, revealing where matter has gathered and, just as importantly, where it hasn't. When astronomers plot these galaxies in 3 dimensions, the cosmic web emerges. Luminous filaments, sprawling superclusters, and between them, the vast dark hollows that mark the voids. To do this, scientists rely on SED-rich surveys, which measure how much a galaxy's light has been stretched as the universe expands. The greater the redshift, the farther away the galaxy is. By combining redshift with sky position, astronomers can pinpoint the location of each galaxy in space. Massive surveys like the Sloan Digital Sky Survey, SDSS, the 2DF Galaxy Redshift Survey, and more recently the Dark Energy Survey, DES, have provided detailed 3D maps of millions of galaxies stretching across billions of light-years. Once the data are collected, sophisticated computer algorithms analyze the distribution of galaxies to identify underdense regions, the cosmic voids. These algorithms look for areas where galaxy density drops below a certain threshold, forming contiguous regions of low density surrounded by denser walls or filaments. Some of these methods include watershed void-finding algorithms, which treat the cosmic density field like a topographic map. High-density regions are mountains, while low-density regions are valleys. The algorithms trace out the boundaries of these valleys, effectively mapping the shapes of voids in 3 dimensions. Spherical underdensity searches, where astronomers look for roughly spherical regions with fewer galaxies than expected, allowing for a simpler statistical analysis. And density field reconstructions, which combine galaxy positions with dark matter simulations to estimate the total matter distribution, including invisible components like dark matter that make up most of the universe's mass. These methods reveal that voids are not uniform bubbles, but complex, irregularly shaped cavities, often interconnected, with smaller voids nested inside larger ones like cosmic Matryoshka dolls. The smallest may only be a few tens of millions of light-years wide, while the largest stretch across hundreds of millions or even up to 1 billion light-years, like the hypothesized KBC Void. Another technique involves using supernovae and standard candles, objects of known intrinsic brightness, to measure how far away certain regions of space are compared to how fast they appear to be expanding. If a region seems to be expanding slightly faster than expected, it could indicate an underlying underdensity, less matter, less gravity, faster local expansion. This technique provides indirect but powerful evidence for voids, since it ties the structure of space to observable expansion rates. Additionally, astronomers study gravitational lensing, the bending of light by gravity. In regions where matter is dense, light from distant galaxies is bent more strongly. In underdense regions, the effect is weaker. By analyzing patterns of weak lensing across the sky, small distortions in the shapes of background galaxies, scientists can map not only visible matter, but also the elusive dark matter that defines the structure of the universe. When lensing maps showed areas with significantly less matter than expected, those regions often correspond to voids in galaxy surveys. In recent years, astronomers have even begun to use the kinematic Sunyaev-Zeldovich effect, which measures how cosmic microwave background photons are scattered by moving galaxy clusters. Variations in the CMB caused by large underdensities can reveal the gravitational fingerprints of voids on the cosmic microwave background itself, offering another layer of confirmation that these structures are real and measurable.
All of these tools together allow scientists to build an increasingly precise map of our cosmic neighborhood. By combining galaxy redshifts, lensing data, supernova distances, and CMB measurements, researchers can identify the large-scale patterns of both density and emptiness, the intricate lattice of the cosmic web. Yet, even with these incredible techniques, detecting voids comes with challenges, especially when we're trying to measure the very one we might be living inside. Because unlike distant voids that can be viewed from afar, the KBC Void surrounds us. We are standing inside the structure we're trying to chart, looking outward from within it. It's a bit like trying to map a vast forest while standing in the middle of the trees. You can see what's nearby, but the overall shape and boundaries are far harder to discern. And that challenge, the problem of perspective, is precisely what astronomers must overcome next. How do we map the structure of something so large and diffuse when we're embedded inside it? How do we distinguish between a local underdensity and a genuine global feature of the universe? Those are the questions that lead us directly into the next part of the story. The observational challenges of detecting cosmic voids, and why measuring one from the inside might be one of the most difficult tasks in all of astronomy. One of the greatest challenges in modern cosmology is that we're trying to measure the shape of the universe from the inside. When it comes to detecting something as enormous and diffuse as the KBC Void, this challenge becomes especially daunting. We are, in essence, living inside the very thing we're trying to map. It's a bit like standing in the middle of a forest and trying to figure out its overall size, shape, and boundaries, while surrounded by trees stretching in every direction, unable to step outside for a better view. When astronomers attempt to chart a void, they rely on seeing the distribution of galaxies from a distant vantage point. For faraway voids, this is possible. We can observe their outlines as regions of space where galaxies thin out or disappear altogether, framed by the denser filaments of the cosmic web. But the KBC Void surrounds us. Every line of sight we have is part of it, meaning there's no outside perspective from which to directly observe its boundaries. Instead, scientists must infer its existence indirectly, piecing together clues from galaxy counts, redshift data, and light distortions that hint at how dense or empty our cosmic neighborhood truly is. One major obstacle is cosmic perspective bias. Because we're inside this potential void, any attempt to measure its size and shape is influenced by our position. It's as if we're standing in a low-lying valley trying to estimate how far the hills rise on the horizon. Our entire frame of reference is curved by the very terrain we're standing in. When astronomers measure galaxy density at increasing distances, they must carefully correct for selection effects, such as how faint galaxies become harder to detect the farther away they are. A local underdensity could easily be mistaken for an observational bias, or vice versa, unless these effects are precisely modeled. Compounding the issue is cosmic variance, the natural variation in density that occurs across different parts of the universe. Even in a universe that's uniform on large scales, smaller fluctuations are inevitable. Distinguishing between a normal local fluctuation and a genuine billion light-year-wide void is no easy feat. To confirm the KBC Void's existence, scientists must show that the underdensity extends far enough, hundreds of millions of light-years in all directions, and that it cannot be explained by random clustering or observational noise.
Another difficulty comes from the limitations of current galaxy surveys. While surveys like the Sloan Digital Survey, or SDSS, and the Dark Energy Survey, DES, have mapped millions of galaxies, they still don't capture everything. Many regions of the sky remain partially unobserved, particularly those obscured by our own Milky Way's disk. This so-called zone of avoidance creates blind spots in our maps of the universe, making it harder to get a complete picture of the galaxy distribution around us. If the KBC Void spans the region beyond our local supercluster and into these obscured areas, its exact shape and depth could remain uncertain for years.
Even when data are available, interpreting them is complex. To measure underdensities, astronomers compare galaxy counts within specific volumes of space to the cosmic mean. But to know the mean, we must already assume something about the universe's large-scale uniformity, a circular problem that cosmologists handle through careful statistical modeling. Too small a survey, and you might mistake a normal fluctuation for a void. Too large a scale, and subtle local features disappear in the averaging process. Then there's the issue of distance measurement accuracy. Redshift, the stretching of light from galaxies as the universe expands, gives us a powerful tool for estimating distance, but it's not perfect. Local motions, known as peculiar velocities, can distort redshift data. Galaxies near large structures like superclusters or voids may move differently from the overall expansion, making them appear closer or farther than they really are. Untangling these effects is incredibly difficult, and any error can ripple through calculations of density and expansion rates, leading to conflicting interpretations of the data. For the KBC Void in particular, this challenge is magnified by its sheer scale. If it truly extends nearly 1 billion light-years, the transition from the underdense region to the denser edge of the void would be gradual. Not an abrupt boundary, but a smooth gradient. Detecting that gradient precisely requires enormous datasets and extremely sensitive instruments. Astronomers must not only measure galaxy densities across vast distances, but also determine how those densities evolve with redshift. Essentially, how the structure of the void changes with time. Despite these hurdles, progress is being made. Improved surveys and new statistical techniques are allowing cosmologists to better estimate large-scale density fields. Machine learning models are being trained to recognize the subtle signatures of voids in galaxy maps, while gravitational lensing data offers an independent way to confirm underdense regions without relying solely on visible galaxies. Still, until we have truly all-sky coverage and unprecedented depth, something upcoming missions like the Vera Rubin Observatory and Euclid will provide, we'll be left with some uncertainty. For now, the KBC Void remains a compelling hypothesis supported by intriguing but not definitive evidence. The difficulty isn't just in proving it exists, it's in proving that we're inside it. And yet, as we face these observational challenges, there's another cosmic clue that ties this story together: the cosmic microwave background, or CMB. The CMB paints the picture of the universe just 380,000 years after the Big Bang, and its remarkable smoothness raises profound questions about how special or typical our cosmic location really is. Could our apparent void fit into that picture of early universe uniformity? That's where the next piece of the puzzle unfolds. The cosmic microwave background, or CMB, is often described as the baby picture of the universe, the oldest light we can see, a faint afterglow left over from the Big Bang nearly 13.8 billion years ago. It's a snapshot of the cosmos when it was just 380,000 years old, long before galaxies or stars had formed, when the universe was a smooth, hot sea of hydrogen, helium, and light. And what that picture shows, above all else, is remarkable uniformity. The CMB tells us that, on the largest scales, the universe is astonishingly homogeneous. The temperature of this background radiation, about 2.725 Kelvin, just a few degrees above absolute zero, varies by no more than 1 part in 100,000 across the entire sky.
That means the young universe was almost perfectly even, with only the tiniest fluctuations in density and temperature. Those tiny ripples eventually grew, under gravity's influence, into the vast cosmic web of galaxies and voids we see today. This uniformity forms the foundation of modern cosmology. It supports what's known as the cosmological principle, the idea that, on large enough scales, the universe looks the same everywhere, and no place is inherently special. We are not at the center of the universe, nor do we occupy a privileged vantage point. The CMB, in its near-perfect smoothness, seemed to confirm this deeply democratic view of the cosmos. But if we truly live inside the KBC Void, a vast region roughly 1 billion light-years wide and 20 to 50% less dense than average, that raises an uncomfortable question. How special is our location, really? If the universe began so smooth and homogeneous, how did we end up in such an enormous underdensity? And does our local environment contradict the principle that we're supposed to be in a typical place? At first glance, the existence of a giant local void might seem at odds with the CMB's smoothness. However, the key lies in the difference between scales. The CMB reflects the structure of the universe when it was extremely young, long before gravity had time to clump matter into the complex web we see today. The variations imprinted in the CMB are seeds of structure, tiny initial fluctuations that, over billions of years, grew into galaxies, clusters, and voids. So while the early universe was smooth, its evolution naturally led to a patchwork of dense filaments and empty spaces. Cosmic voids, including potentially massive ones like the KBC Void, are expected features of that later structure. Even so, the KBC Void stands out for its scale. Most voids are tens to hundreds of millions of light-years across. 1 billion light-year wide underdensity near our location would be unusually large, though not necessarily impossible. The question then becomes, does this violate cosmic homogeneity, or could it still fit within the expected statistical variations of the universe's structure? Current cosmological models suggest that such a massive underdensity is unlikely, but not entirely forbidden. The universe is, after all, a statistical system. Not perfectly uniform, but roughly so on average. If we zoom out far enough, everything evens out. So even if we do inhabit a large void, it doesn't mean we're in a cosmically special place. It could simply be one of the natural fluctuations that emerged from those tiny CMB ripples long ago. However, this raises another subtle issue. Because the CMB gives us a snapshot of the entire observable universe, it also provides a reference frame, a cosmic rest frame of sorts. If we were truly sitting in an unusually large void, we might expect to see faint signatures of that fact in the CMB itself. These could appear as anisotropies, slight directional differences in temperature or polarization caused by the gravitational effects of our local environment. Indeed, some anomalies in the CMB, such as the so-called CMB cold spot, have been studied in this context. Some researchers speculate that such features might hint at the influence of a nearby supervoid, though the evidence remains inconclusive. The overall smoothness of the CMB, however, places strong constraints on how extreme our local underdensity can be. If the KBC Void were too deep or too large, its gravitational effects might produce distortions in the CMB that we don't observe. That means if the void does exist, it must be relatively gentle, subtle enough to affect local expansion measurements, but not dramatic enough to leave an obvious scar on the cosmic microwave background. This delicate balance between the CMB's global uniformity and the local unevenness implied by the KBC Void perfectly encapsulates the beauty and complexity of cosmology. The universe can be both smooth and structured, both uniform and wildly varied, depending on how far you zoom out. The CMB gives us the big picture, while local voids and clusters fill in the intricate details.
Still, the CMB's message is clear. On the grandest scales, the universe is consistent, predictable, and remarkably balanced. If we do live inside a void, then it's a local quirk of cosmic geography, not a violation of the universe's broader order.
We might occupy a slightly emptier region of space, but we're still part of the same cosmic tapestry that began with those faint, nearly uniform ripples in the ancient light of creation. And intriguingly, when scientists look more closely at modern data, galaxy counts, supernova brightness, and large-scale structure surveys, they find subtle but consistent hints that our local region really might be underdense. Evidence that seems to support, at least in part, the idea of the KBC Void. Over the past decade, a growing number of independent studies have gathered hints that our corner of the cosmos may in fact be less dense than average, subtle but persistent signs that lend weight to the KBC Void hypothesis. These findings don't shout their conclusion, they whisper it, emerging from careful analyses of galaxy surveys, supernova brightness, and cosmic flow measurements that all seem to point in the same direction. We may be living in an unusually empty patch of the universe. One of the earliest and most direct pieces of evidence comes from galaxy counts, simply tallying how many galaxies exist within certain distances and comparing those counts to what we would expect based on cosmological models. Ryan Keenan and his colleagues in their original 2013 study analyzed data from near-infrared surveys, such as the 2-mass redshift survey and the UKIDSS Large Area Survey. They measured galaxy density within concentric shells surrounding the Milky Way, extending out to nearly 1,500 megaparsecs, roughly a billion light-years. What they found was striking. The number of galaxies within about 300 to 400 megaparsecs, about 1 billion light-years, was 20 to 50% lower than the density observed farther away. Beyond that distance, the counts leveled off, matching the expected cosmic average. This pattern, a significant local underdensity surrounded by a more typical cosmic environment, is precisely what one would expect if the Milky Way resides near the center of a giant void. It doesn't mean the void is perfectly spherical or completely empty, rather it suggests a gradual transition from a locally sparse region to denser space beyond. Further support came from studies of Type A supernovae, the standard candles of cosmology. Because these stellar explosions have nearly uniform intrinsic brightness, astronomers can use them to measure cosmic distances and expansion rates with remarkable precision. Several analyses, including those by researchers like Benoit Laveau, Stephen Appleby, and David Wiltshire, found that nearby supernovae appear slightly brighter than expected compared to those farther away. This brightness difference implies that light from those supernovae has traveled through a region of lower matter density, a region where the universe's local expansion rate is faster than average. In simpler terms, if you live inside an underdense region, space itself is expanding just a little more quickly. Light from nearby supernovae therefore travels through that faster expanding space, making them appear closer, or brighter, than they would if the universe were perfectly uniform. These supernova observations align remarkably well with the kind of underdensity proposed by the KBC Void model. Another line of evidence comes from the study of cosmic flows, the peculiar velocities of galaxies as they move under the gravitational influence of large-scale structures. Galaxies in denser regions tend to be pulled inward toward massive clusters, while those in voids drift outward as space expands more freely. Measurements of local galaxy motions, such as those compiled in the Cosmic Flows 3 catalog, suggest that our region of space is part of a slow, outward-moving flow consistent with the dynamics of an underdense environment. The motion of galaxies around the local void, a smaller void adjacent to the local group, also supports this picture of our galaxy's neighborhood being less crowded than average. Then there's evidence from radio and infrared galaxy surveys, such as those conducted with the Wildfield Infrared Survey Explorer, WISE, and the Arecibo Alfalfa Survey, which detect galaxies through their gas and infrared emissions rather than visible light. These surveys, less affected by dust obfuscation, confirm that large portions of the sky contain fewer galaxies than expected in certain redshift ranges. This consistent underdensity in multiple wavelength regimens strengthens the argument that the effect is real, not just an artifact of missing data. Even more intriguingly, CMB lensing and gravitational potential studies have revealed slight but measurable evidence that our local region is less massive than average. Light from the cosmic microwave background is subtly deflected by the gravitational fields it encounters along its path. By analyzing how this light bends, scientists can reconstruct a map of the total mass distribution, including dark matter, across the sky. Several of these reconstructions, particularly those comparing Planck satellite data with large-scale galaxy surveys, show hints of a mild underdensity in our local region consistent with the KBC Void's predicted profile. Taken together, these different strands of evidence, galaxy counts, supernova brightness, peculiar velocities, and gravitational lensing, form a picture that's difficult to dismiss. None of them on their own provide definitive proof, but when viewed collectively, they weave a consistent narrative that our local universe appears to be a little emptier, a little lighter, and expanding a little faster than the cosmic average. Of course, every observation in astronomy comes with uncertainty. Data interpretation depends on assumptions about calibration, cosmic evolution, and model fitting. Yet the persistence of this pattern across multiple independent datasets makes the KBC Void hypothesis more than a mere curiosity. It's a legitimate possibility, one that fits the available evidence without requiring entirely new physics. Still, as every scientist knows, extraordinary claims demand extraordinary evidence. For every study that finds signs of a local underdensity, there are others that challenge its significance or even its existence. To paint a balanced picture, we must now turn to the skeptics, those researchers who argue that the evidence for the KBC Void may not hold up under closer scrutiny.
While the KBC Void hypothesis has captivated many with its elegant simplicity, offering a natural, local explanation for puzzling cosmic observations, not all astronomers are convinced. In fact, a significant number of studies have challenged the idea that we live in a void large or deep enough to meaningfully affect cosmic expansion measurements. These researchers argue that the apparent underdensity around us may either be an illusion of limited data or simply a normal statistical fluctuation within the cosmic web, rather than evidence of a vast billion light-year wide bubble. The first major line of skepticism comes from improved galaxy redshift surveys. As datasets grew larger and more complete, researchers began to revisit the original conclusions drawn by Keenan, Barger, and Cowie. Studies using data from the Sloan Digital Sky Survey, SDSS, the 6DF Galaxy Survey, and the DESI Legacy Survey found that while there are indeed modest local variations in galaxy density, these differences tend to average out beyond a few hundred million light-years. In other words, the underdensity may exist, but it appears to be shallower and smaller than the KBC team initially estimated. One particularly influential study came from Whitbourne and Shanks, 2014, who analyzed data from the 6DF and SDSS surveys. They found hints of a local underdensity in one region of the sky, specifically toward the southern galactic cap, but not uniformly in all directions. This asymmetry suggested that the local universe isn't defined by a single spherical void, but rather by patchy variations in density that are well within the expected range of cosmic variance. Their conclusion was cautious but clear. While local inhomogeneities exist, they're unlikely to be large enough to have a significant impact on the measured expansion rate of the universe. Subsequent work reinforced that view. In 2019, a comprehensive analysis by Kenworthy, Skolnick, and Rees, part of the SHOES collaboration, which measures the Hubble constant using type A supernovae, found that local density variations cannot explain the Hubble tension. Their data, which covered distances out to about 1.5 billion light-years, showed that even if the Milky Way were at the center of a mild underdensity, its effect on the Hubble constant would be less than 1%. The observed tension, however, is about 9%. In short, a void like the one proposed by the KBC team could slightly nudge the numbers, but not fix the problem. A similar conclusion came from Hasselbauer et al. 2020 and Sarkar et al. 2021, who ran detailed cosmological simulations. These models recreated the large-scale structure of the universe and then placed virtual observers in different types of regions, dense clusters, average zones, and deep voids to see how their measurements of expansion would differ. The results showed that while observers inside voids do measure slightly higher local Hubble constants, the difference is far too small to match the real-world discrepancy. The simulations indicated that a void large enough to produce the observed Hubble tension would be so extreme that it would contradict the homogeneity implied by the cosmic microwave background.
Another major argument against the KBC Void hypothesis comes from gravitational lensing data and CMB analyses, which show no strong signs of a massive local underdensity. If a void spanning nearly 1 billion light-years truly surrounded us, it would have subtle but measurable effects on both the bending of light from distant galaxies and the anisotropies in the cosmic microwave background. So far, those signatures have not been observed at the expected strength. The Planck satellite's precise measurements of the CMB, for instance, shows a universe that is impressively consistent with large-scale homogeneity. Additionally, researchers studying the kinematic Sunyaev-Zeldovich effect, the distortion of the CMB caused by moving galaxy clusters, have placed upper limits on how large and deep a local void could be without leaving detectable imprints on the background radiation. The observed data suggests that any local underdensity must be relatively mild, likely too mild to affect the local Hubble constant meaningfully. Critics also point out a philosophical issue with the KBC Void hypothesis. If we truly live near the center of such an enormous structure, it might imply a special location in the universe, something that contradicts the Copernican principle, which asserts that we do not occupy a privileged or central position. While being near the center of a void could happen by coincidence, the statistical odds are low. Most cosmologists are therefore reluctant to accept an explanation that places us in such an exceptional position unless the evidence is overwhelming. In summary, the opposing evidence paints a more conservative picture. The local universe does appear to be somewhat underdense, but not enough to explain the Hubble tension. Large-scale surveys find that density fluctuations on scales of 1 billion light-years are rare and smaller than initially reported. The smoothness of the CMB and the lack of corresponding lensing signals suggest that any void around this is modest at best. Cosmological simulations show that such a massive underdensity would likely contradict the broader uniformity of the universe. So while the KBC Void remains an intriguing and scientifically valuable hypothesis, many researchers now see it as a partial contributor at best, not a complete explanation. It may account for a fraction of the observed discrepancy in the Hubble constant, but the rest likely arises from other factors, perhaps new physics, evolving dark energy, or unknown observational biases. Yet even if the KBC Void turns out to be less dramatic than first imagined, the very idea has forced cosmologists to look more critically at their assumptions. It reminds us that our place in the universe may influence how we interpret it, and that perspective matters, even on cosmic scales. And that perspective naturally brings us to a deeper, more philosophical question, one that reaches beyond the numbers and into the meaning of our cosmic situation. What does it mean if we really are living inside a void? How would that change the way we see ourselves in the grand tapestry of the universe? If the KBC Void or any large-scale underdensity truly surrounds us, then its significance goes far beyond cosmological measurements and equations. It strikes at something deeper, our very sense of place in the universe. For centuries, astronomy has gradually displaced humanity from one imagined center after another. First from the center of the Earth, then from the center of the solar system, then from the center of the galaxy, and finally from any notion of being in a special part of the cosmos. This steady dethronement, guided by the Copernican principle, has shaped the foundation of modern science, the assumption that our position is typical, our perspective average, our environment representative of the universe as a whole. But what if that isn't entirely true? What if, despite all our efforts to shed cosmic self-importance, we find ourselves in a place that is, statistically speaking, a little unusual? Living inside a vast cosmic void doesn't make us cosmically central or privileged, of course. It doesn't mean the universe was designed around us or that we are special in any existential sense. But it does suggest that our immediate neighborhood may not be the average sample we've long assumed it to be. The cosmic average, that concept of a perfectly typical, evenly filled universe, may only exist in theory. In practice, the cosmos is messy, lumpy, and structured. And we, it turns out, might live in one of its quiet, rarefied outskirts rather than its bustling core. This realization invites a profound shift in perspective. For much of cosmological history, scientists have relied on the idea that the universe is homogeneous, that any observer anywhere would see roughly the same large-scale structure and expansion. It's a principle of humility, meant to guard against anthropocentrism. But discovering that we live in an underdense region means we must carefully account for our location when interpreting the universe's behavior. The view from nowhere, a perfect, objective vantage point, may not actually exist. In philosophical terms, this is an echo of an ancient tension between realism and perspectivism. Realism tells us that the universe is what it is, independent of our place within it. Perspectivism reminds us that every observation, every cosmic measurement, is filtered through our position, our instruments, and our limitations. The void hypothesis brings these two ideas into direct dialogue. We strive to measure the universal constants, but our very presence inside a giant low-density region could subtly distort those measurements. We are, in effect, cosmic observers trapped in a kind of gravitational mirage, trying to infer the whole from within one of its hollows. On a more emotional level, the notion of living inside a void also reshapes our relationship to the universe's vastness. For much of human history, we've associated emptiness with loneliness or insignificance. To think that our galaxy floats in one of the emptiest regions of the cosmos might seem unsettling, a poetic reflection of our isolation in an infinite universe. Yet it's also strangely fitting. Life, fragile and rare, emerging in a quiet pocket of space, surrounded by darkness and silence, there's something almost poetic about that image. It also invites us to question what we mean by typical. Perhaps there is no truly typical place in the universe. Every location, whether inside a dense cluster of galaxies or a vast void, experiences its own version of cosmic reality. In that sense, the universe may be like a great symphony, with each region playing a slightly different note, yet composing a coherent whole. The idea that our measurements might differ because of where we happen to reside doesn't diminish our understanding, it enriches it. It reminds us that observation is always an act of participation. Moreover, being inside a void might actually be a cosmic advantage. Dense regions, full of galaxy clusters and active galactic nuclei, are tumultuous and energetic places, filled with radiation, collisions, and gravitational turbulence. Our relatively tranquil environment could be part of what made the long, stable evolution of our galaxy and ultimately life itself possible. In that sense, cosmic emptiness might be the ultimate cradle of existence. So perhaps instead of seeing a void as a place of absence, we might see it as a space of balance, a region calm enough for stars to live long, for galaxies to evolve peacefully, and for observers like us to emerge and wonder about the structure of it all. The universe, after all, needs both light and shadow, density and emptiness, to exist in its full complexity. In the end, whether we inhabit a truly massive void or just a mildly underdense patch of the cosmic web, the philosophical lesson remains. We are not perfect, detached spectators of the universe. We are embedded within it. Our perspective is shaped by our environment, and even the most advanced cosmological measurements are colored by the context of our cosmic home. This humility, recognizing both the limits and the beauty of our cosmic perspective, is at the heart of modern cosmology. It pushes us to refine our theories, to question our assumptions, and to look deeper into the structure of the universe to understand what's truly universal and what's simply local. And that brings us to an even more practical question, one that blends philosophy with physics. If the KBC void does exist, how would confirming it reshape our cosmological models? What would it mean for our measurements of dark energy, the Hubble constant, and the very parameters that define the fate of the universe? If the KBC void were confirmed to exist, and not just as a modest local underdensity, but as a billion light-year-wide structure with significant gravitational and observational influence, the implications for cosmology would be profound. Such a discovery would ripple across multiple areas of astrophysics, from our understanding of the universe's expansion to the inferred properties of dark energy, and even the philosophical foundations of the cosmological principle itself. It wouldn't merely add another data point to the cosmic map, it would force us to rethink how we interpret the map entirely. To begin with, confirming the KBC void would demand a revision of local cosmological parameters, the numbers that define how the universe behaves in our region of space. The most immediate effect would be on the Hubble constant, HO, which describes how fast the universe is expanding. If we truly live inside a large underdensity, the local expansion rate we measure is not the universal average. It's a locally biased value, inflated because our region is expanding faster than the denser surroundings. This means the Hubble tension, the ongoing mismatch between local measurements around 74 kilometers per second per MPC and the early universe measurements from the cosmic microwave background around 67 kilometers per second per MPC could be partially or even mostly explained by our position. Correcting for the void's gravitational influence would shift our local measurements closer to the true cosmic average, potentially bringing the two into better alignment. The implications wouldn't stop there. The inferred properties of dark energy, the mysterious force driving the acceleration of the universe's expansion, would also be affected. Currently, cosmologists interpret the observed acceleration as evidence that about 68% of the universe's total energy density is in the form of dark energy, an unknown entity that acts like a repulsive pressure, counteracting gravity on large scales. But if part of the observed acceleration is an illusion caused by our position inside an expanding void, then the actual contribution of dark energy to the universe's dynamics might be smaller than we think. In essence, the void could be mimicking some of the effects attributed to dark energy. We might be overestimating how much dark energy there is because we're observing from a region that naturally expands faster than average. In cosmological models, this would translate into a slightly lower omega lambda, the parameter representing dark energy density, and potentially a small adjustment to omega matter, the matter density parameter. The overall shape of the Friedmann equations, which govern cosmic expansion, wouldn't change, but the specific balance between matter, radiation, and dark energy could shift. This would ripple through our understanding of the universe's age, size, and ultimate fate. Even the cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales, would need to be revisited, or at least refined. Confirming that we live inside a billion light-year scale void would mean homogeneity is an approximation, not an exact reality, even on scales previously assumed to be smooth. The universe might still be statistically uniform overall, but with significant local deviations that can't be ignored in high-precision cosmology. This wouldn't necessarily overturn modern cosmology, but it would push it toward a more relativistic, locally dependent model of observation, one that accounts for the fact that cosmic measurements are always made within a particular gravitational environment. Models like the Lemaitre-Tolman-Bondi solution, which describes spherically symmetric but inhomogeneous universes, would gain renewed relevance. These models allow cosmologists to explore how local structures like voids affect observable quantities such as redshifts, luminosity distances, and time dilation. If validated, the KBC void could also impact our interpretation of cosmic variance, the idea that different observers in different parts of the universe might measure slightly different values for cosmological parameters simply due to natural fluctuations in density. This would mean that there's no single absolute Hubble constant, only local and global averages that differ by small but measurable amounts. Such a realization would add nuance to the concept of a universal expansion rate, showing that even the cosmos allows for perspective. Furthermore, large-scale structure models, simulations of how matter clumps and empties over cosmic time, would need to incorporate the KBC void as a significant feature. The existence of such a large underdensity could offer insights into structure formation and the distribution of dark matter. For example, if the KBC void formed naturally within the lambda-cold dark matter framework, it could help refine our understanding of how matter migrated across the cosmic web during the universe's evolution. If it couldn't be explained within that framework, it might hint at new physics, perhaps involving non-standard dark energy behavior or early universe fluctuations that grew larger than expected. Even observational strategies would change. Cosmologists would need to correct local measurements, like those based on Type A1 supernova, Cepheid variables, and baryon occulence oscillations, BAO, for the influence of the void's geometry and density. This would improve precision in determining global cosmological constants and reduce systematic biases.
In short, confirming the KBC void wouldn't break the standard model of cosmology, it would refine it, grounding it more firmly in the messy, structured reality of the universe. Just as Einstein's general relativity refined Newtonian gravity without replacing it, the KBC void would add a layer of context to cosmic measurements, reminding us that our data are not gathered from a uniform canvas, but from within a complex, evolving cosmic web. And yet, This refinement would lead naturally to a broader realization that our universe, though uniform on average, is never perfectly so. Local differences like voids and clusters are part of a cosmic variance that we must learn to live with. In fact, understanding that variance and how our particular position fits within it might hold the key to the next generation of cosmological precision. Which brings us directly to the next idea, cosmic variance itself. The built-in irregularity of the universe and how our location within that grand imperfection may forever shape what we observe. In cosmology, there's a quiet acknowledgement that the universe, for all its mathematical elegance and sweeping uniformity, is never perfectly even. It's textured, imperfect, and beautifully uneven. This natural irregularity, the subtle differences in matter distribution across space, is what scientists call cosmic variance. Cosmic variance is, in essence, a recognition that no two places in the universe are exactly alike. Even if the cosmos is homogeneous on the largest imaginable scales, it's still laced with fluctuations. Galaxies clumped together here, vast voids stretching there. These are not errors or exceptions, they are features of how the universe evolves. Gravity amplifies the smallest initial differences, turning faint ripples in the early density field into the rich three-dimensional cosmic web we see today. In that sense, cosmic variance is not a flaw in cosmology, it's its fingerprint. It reminds us that while we can speak of an average universe, we can never directly observe it. Every measurement we make comes from one small vantage point within a larger, varied whole. This concept becomes profoundly relevant when we talk about the KBC Void. If our galaxy resides in a region that's underdense by 20 to 50%, that's not an anomaly so much as a reflection of cosmic variance itself. Voids and clusters are expected outcomes of the universe's growth from small quantum fluctuations after the Big Bang. Some regions became overpopulated with matter, forming galaxy clusters and filaments, while others thinned out into vast, near-empty expanses. The cosmic web, that immense network of structure, is the physical manifestation of cosmic variance on a grand scale. However, while cosmic variance explains why voids exist, it also introduces a fundamental limit on what we can know. Because we can observe only from our single location in space and time, our perspective is inevitably biased by the local conditions of our environment. This means that our estimates of cosmological parameters, like the Hubble constant, dark energy density, and matter content, might always carry a slight uncertainty, not because our measurements are flawed, but because our cosmic vantage point is not perfectly representative of the universe as a whole. To put it another way, the universe has only one observable instance, the one we're in. And our cosmic sample size is by definition 1. We can't step outside the universe to take a second measurement from a different location for comparison, so if we happen to live in a region that's denser or emptier than average, our observations of distances, redshifts, and expansion rates will reflect that bias. That's the unavoidable truth of cosmic variance. The KBC Void hypothesis takes this idea and grounds it in something tangible. Instead of assuming our local patch is exactly average, it suggests we might occupy one of the naturally occurring underdense zones of the cosmic web. This would make our observations slightly different than what a hypothetical observer might measure from a denser region billions of light years away. And if we acknowledge that, then part of the so-called Hubble tension could simply be a manifestation of cosmic variance at work. Astronomers have already incorporated this concept into their statistical models. When large-scale surveys report measurements of the Hubble constant or the density of matter, they include an uncertainty term that accounts for cosmic variance, typically around 1 to 2%. But if our local environment is more extreme than average, as the KBC Void suggests, the effect could be larger than that. We might be underestimating how much local structure can bias our view of the universe's expansion. It's a humbling thought. Even with the most precise instruments and mathematical models, there are limits to what we can know from within our small patch of the cosmic web. No matter how advanced our technology becomes, our perspective will always be filtered through the lens of our local cosmic geography. Yet, cosmic variance is also a beautiful idea, because it means that every galaxy, every cluster, and every observer in the universe experiences their own slightly unique version of reality. For an observer living inside a massive cluster, the cosmic microwave background might look a little bit different. The expansion rate might seem slower. The gravitational pull of their surroundings might subtly alter the shape of spacetime itself. For us, perhaps, the story is the opposite. We live in a quiet, thin region where space expands more freely, and where the universe looks just a little bit faster, a little bit lighter. Ultimately, cosmic variance teaches us humility and patience. It reminds us that the universe is not a perfect laboratory. It's a dynamic, living structure filled with local peculiarities and grand averages woven together. Our task as cosmologists isn't to eliminate these variations, but to understand them, to learn how local structure, like the KBC Void, fits into the larger cosmic picture. And that understanding is rapidly advancing. With the new generation of observatories and missions on the horizon, astronomers are preparing to map the cosmos in unprecedented detail, to determine, once and for all, whether our local patch is truly a vast void or merely an illusion of limited observation. These upcoming surveys will provide the data needed to test the KBC hypothesis with stunning precision. Which brings us to the next step in our journey. What's next for the search? What tools and missions will finally allow us to confirm or refute the existence of the KBC Void? And what new secrets might they reveal about the structure of the universe itself? The question of whether we truly live inside a vast cosmic void, the KBC Void, may soon be answered. For decades, astronomers have worked with limited data, constrained by the boundaries of existing galaxy surveys and the faintness of the farthest cosmic structures. But the next generation of observatories is poised to change that. With an unprecedented depth, resolution, and sky coverage, these instruments will allow us to map the universe in exquisite detail, to trace its filaments, measure its voids, and determine, once and for all, whether our cosmic neighborhood is truly as underdense as it seems. At the forefront of this new era stands the Vera C. Rubin Observatory, nestled high in the Chilean Andes. Scheduled to begin full science operations soon, the Rubin Observatory's Legacy Survey of Space and Time, LSST, will revolutionize our view of the cosmos. Over its 10-year mission, it will capture roughly 20 billion galaxies, mapping almost the entire visible sky in motion and depth. Unlike previous surveys which measured galaxies in isolated snapshots, LSST will track their positions and brightness over time, providing a 3D map of the universe that stretches across tens of billions of light-years. This means that astronomers will be able to construct a highly detailed density map of our local cosmic environment. They'll identify precisely where galaxies cluster and where they don't. If the KBC Void truly exists, the LSST will reveal its structure in fine detail, its size, its gradient, and whether the Milky Way lies near its center or along its edge. The survey's ability to detect faint distant galaxies will also help resolve one of the biggest challenges in current studies: the completeness of galaxy counts. No more guessing at what lies behind dust, distance, or data gaps. LSST will fill those holes with real observations. Complementing Rubin's ground-based vision is a powerful eye in space, the Euclid mission launched by the European Space Agency. Euclid's goal is to unravel the mysteries of dark energy and dark matter by precisely mapping the three-dimensional structure of the universe out to 10 billion light-years. Using its 1.2-meter space telescope, Euclid will survey billions of galaxies across one-third of the entire sky, measuring their shapes, distances, and clustering patterns with extraordinary accuracy. For the KBC Void hypothesis, Euclid will be invaluable. Its sensitivity to gravitational lensing, the bending of light by matter, allows it to map not just visible galaxies, but the dark matter density field that underlies them. This means that Euclid won't just count galaxies, it will weigh the universe itself. If our region is truly underdense, Euclid will see that directly in the weak lensing data, as a corresponding dip in the mass density near our cosmic location. Meanwhile, NASA's Nancy Grace Roman Space Telescope, set to launch later this decade, will complement both Rubin and Euclid by observing even deeper into specific regions of the sky. Roman's high-precision infrared instruments will allow astronomers to measure distances to Type 1a supernovae, those cosmic standard candles, used to track expansion, with unprecedented accuracy. By comparing supernovae distances across different regions of space, scientists will be able to determine whether our local expansion rate is truly faster than average, as predicted if we reside inside a void. Together, these observatories will form an unprecedented cosmic triangulation network. Rubin will provide the wide-field galaxy maps, Euclid will supply the dark matter scaffolding, and Roman will refine the distance ladder with exquisite precision. By combining their data, cosmologists will be able to measure local underdensities, cosmic flows, and expansion rates in exquisite detail,
enough to either confirm or decisively rule out the KBC Void as the source of the Hubble tension.
Beyond these flagship missions, other surveys are also set to contribute. The Dark Energy Spectroscopic Instrument, DESI, is already mapping the redshifts over 35 million galaxies and quasars, providing the most detailed 3D picture of the cosmic web ever constructed. The Square Kilometer Array, SKA, once fully operational, will use radio waves to trace hydrogen gas across vast distances, allowing scientists to detect faint galaxies that optical telescopes might miss, especially in the so-called zone of avoidance behind our own Milky Way. All of these efforts share one goal: to see the universe not just as it appears, but as it truly is. To peel back the layers of observation and bias and reveal the authentic large-scale structure of space-time. Whether the result supports or refutes the KBC Void, the outcome will be transformative. If these surveys confirm the void's existence, it will mark one of the most profound realizations in modern cosmology, that our measurements of the universe's expansion have been shaped by our location within it, and that even cosmic constants may not be as constant as we assumed. It would bring closure to decades of debate over the Hubble tension, explaining at least part of the discrepancy without invoking exotic new physics. If, on the other hand, these missions find that the KBC Void is too small or too shallow to have any measurable impact, that will be equally momentous. It would push us to look beyond local structure, toward new physics, new forms of dark energy, or modifications of gravity itself, to explain the universe's accelerating expansion. Either way, our understanding of cosmology will be sharpened and deepened. In many ways, the coming decade will be a turning point, a time when humanity finally sees the cosmic web in its full complexity, from its bright filaments to its hauntingly empty voids. The tools are ready, the data are on the way. What remains is to interpret the results, and in doing so, redefine our place in the grand structure of the cosmos. Because whether we're perched inside a vast cosmic hole or floating in an ordinary patch of space, what these surveys will reveal goes beyond mere measurement. They'll tell us what kind of universe we live in, and perhaps even, in a small but profound way, why we're here to observe it at all. Even if future surveys ultimately confirm that we live inside a vast cosmic hole, a billion light-year wide, underdense bubble in the grand web of the universe, the truth is, it doesn't make our home any less extraordinary. In fact, it might make it more so. Because even a void, even the most silent, seemingly empty region of space, is still part of something immeasurably vast, alive, and connected. The KBC Void, if real, isn't a lonely island in the universe. It's one note in an endless cosmic symphony, one pocket in the infinite texture of creation. Our galaxy, the Milky Way, still hums with stars. It still orbits in its graceful spiral, surrounded by billions of others. Beyond it, clusters still gather, filaments still stretch, and light from distant galaxies still threads its way through the dark. The emptiness around us isn't isolation. It's part of the balance that defines the universe's architecture. The cosmic web needs its voids as much as it needs its clusters. The quiet expanses give contrast to the luminous bridges of galaxies. Without the dark spaces, the bright ones would lose their meaning. In a way, the idea that we might live inside a cosmic void mirrors the human condition itself. We find meaning not in perfection, but in perspective, in recognizing our place within something larger, something we can't fully comprehend. Whether our local universe is slightly emptier or more crowded doesn't change the fundamental truth that we are of the universe, made of its atoms, shaped by its gravity, and illuminated by its light. The void, if it exists, isn't a separation, it's a context. What's more, this discovery, if it holds, is not a limitation of our understanding, but a sign of its growth. A century ago, humanity didn't even know there were other galaxies. 50 years ago, we couldn't see beyond the Milky Way's neighboring clusters. Today, we're talking about measuring subtle density gradients across billions of light years and detecting underdensities that influence the expansion of the universe itself. Every step forward refines our understanding, and every mystery we uncover opens another window into the cosmic story. Even if we are inside a cosmic void, it's worth remembering that voids are not nothingness. They contain galaxies, gas, dark matter, and light. They evolve, expand, and shape the universe's fate just as much as the dense regions do.
The emptiness is only relative. It's a different kind of fullness, one defined not by what's present, but by the subtle gravitational relationships that stretch across the cosmic web. And perhaps that's the deeper lesson of the KBC Void, that the universe doesn't just expand around us, it expands through us. We're not passive observers sitting in a special or isolated place. We're participants in the same cosmic dance that began with the Big Bang. Whether we're living in a cluster or a void, the universe is still expanding, still evolving, and still inviting us to look deeper.
So even if we are inside a billion light-year wide cosmic bubble, even if our galaxy drifts through one of the quietest regions of the universe, it's still part of an interconnected whole, woven from the same laws of physics, the same cosmic fabric, the same story that binds every star and every atom. We're still connected to galaxies billions of light years away, through gravity, through light, through time. The void doesn't separate us from the universe. It reminds us that we belong to all of it. And that's the ultimate perspective. Whether we live in a crowded cluster or a quiet void, we are and have always been part of the same cosmic journey. A journey that began in light, continues through the vastness of time, and will keep unfolding long after our species, our planet, and even our galaxy have passed. Our understanding of that journey is still evolving. We don't yet know if the KBC Void is real, or if it's just another step towards something even deeper waiting to be discovered. But one thing is certain, the more we learn, the more wondrous the universe becomes. In the end, whether our home lies in a cosmic void or not, we are part of a living universe, vast, interconnected, mysterious, and profoundly beautiful. And the fact that we can ask these questions, that we can measure and wonder, and reach across the stars for answers, may be the greatest sign of all, that the universe, empty or not, is anything but void. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.